Perfect. Okay. Yeah, thanks again for your kind introduction. Today, what I would like to do is I would share a bit of ideas about our research, and that relates to generative AI in chemical engineering, in particular in process engineering. And I will also show one application later on where we try to do autocorrection for chemical process flow sheets. But let me start a bit more high level first. So you're all aware that's why you're here, right? That GenAI led to breakthroughs in multiple other domains, generating text, images, videos, and maybe a bit more close to our domain, to chemistry, also generating molecules or protein structures and so on. However, what I do in my research is I focus on process engineering, and there has actually been not too many advances yet with GenAI. So what I would like to talk to you about is how would it feel like, how would it look like to have GenAI in our domain? What does it take to develop it? I guess you will have a few days in the hackathon afterwards to actually work on it, try out stuff your own. And I would like to talk a bit about, is it feasible? And then I guess you will continue on that stuff. So I hope to get some feedback on what your results are as well. Before I start to talk about process engineering, I want to highlight 3 existing applications and exciting applications of GenAI in other domains. And I guess everyone here is aware of all 3. The first one being GitHub Copilot, which is auto-completion of code. So this is used by software developers to develop software quicker, where you can basically start with a comment or basically start with the first line of your code, and this auto-completion will kind of guess what comes next. And it's believed that these kind of technologies will accelerate software development by a factor of approximately 2 in the future. So it's really transformative effect on how quick you can deliver software, develop software, and also in terms of reducing cost for development as well. The second one is machine translation. So these are examples like DeepL, Google Translate, where you can now easily translate from one language to another. I myself use it quite frequently. And here, again, we have this transformative aspect, right? So we can solve problems that we haven't been able to solve before. So I can now translate a text from Japanese to Chinese in a matter of seconds to really high accuracy or quality for really little money, right? So most of these tools you can use for free if you want to translate a whole book talking about euros, but nothing compared to hiring a person translating that stuff manually, which would take way more time and money, of course. And third one being autocorrection of text. This is Grammarly, for example, where you can automatically check your text not only for spelling errors, but also for how to reformulate text to make it more effective, deliver your message better, and so on. And if I look at it, of course, it may be only a small step from what we had before in terms of autocorrection. I believe it's actually a significant step already. But putting all of that together, comparing that to manually correcting, editing books, also there's a huge advantage as well of using these tools. And behind all of these 3 tools, there is usually a machine learning, a GenAI, transformer architecture, and sometimes combined with rules as well. But again, I don't want to talk too much about what's out there in terms of GenAI in other domains. I would make the bridge to our domain, to process engineering. And this is just a few examples. What I really want to do is basically go beyond just applying GenAI on text. So I want to encourage you to, if you think about GenAI, don't think about ChatGPT being applied to more different text from our domain. I want to turn it around, take the application view and be like, hey, this is the kind of job that is done every day. How can we envision GenAI helping me here? And don't restrict yourself to text. So what we do is we work a lot with engineering documents, with piping and instrumentation diagrams, process flow diagrams, and so on. And I try to translate these concepts to these diagrams to the engineering workflow. So if we talk about autocompletion of code, of text, what we think of is autocompletion of flow sheets. So how can we actually help engineers to develop their chemical processes quicker? And that relates to the topology of the flow sheet, but also to all the specifications, like what kind of material should you use, how should you operate a plant, and so on. So a tool to support engineers to make these decisions quicker using GenAI. If we talk about translation between one language and another one, what we foresee is considering different engineering stages of these diagrams as different languages and building algorithms to translate between them. So basically learn what the engineers or what the engineers are doing. And here the vision is, hey, can we somehow translate from the PFD level information, and that's not only the diagram, that's also the supporting information and documentation, to P&ID level information, or from P&ID level to more detailed P&IDs and so on. So can we support engineers with these suggestions as well? And the last one is probably very obvious now, right? So we also want to have autocorrection of P&IDs. So we want to be able to automatically capture errors in P&IDs, make suggestions how to improve that. And that's not only limited to actual errors, that could be also including stuff that we can just do better, right? So if we change the control architecture here, can we control the process better? Can we make it more safe? Can we make it more efficient? So this kind of stuff, and that's extremely important considering that P&IDs have, 2,000 pages maybe, 800 symbols per page. So it gets quite messy. It's a lot of work to do that manually. And of course, the earlier you detect those errors, the more money you save, and maybe even the more health or safety risks you avoid. Talking about safety, there's another application that we work on. We have a PhD on this topic as well. We say, hey, how can GenAI help us to generate HAZOPs or co-generate HAZOPs with us together? So also here we're talking about assistance. We're not replacing the engineers. We're thinking about, okay, having all this information, having all the old HAZOP reports, can we generate HAZOPs automatically to support the HAZOP process, to reduce the cost, increase quality of this? So these are kind of the 4 examples that I wanted to bring up to, and there's many more you can think of, many more we look into actually. But just to give you an idea of, hey, that's how it could feel, that's how it could look to have GenAI in the process engineering domain. And now the question is, how can we get there, or are we actually already there? And the obvious idea is, hey, can I just call ChatGPT, ask ChatGPT our engineering questions like, hey, can you help me to design this process? And then, get the answer, be done. If we do that, we get a positive reply. So that's the good news, right? So certainly I can help you. And ChatGPT also recognizes, hey, you are talking about images here, so we need to generate these diagrams. It takes a second, you know that. And then what happens is we get the result back. And for those of you who are somehow related to chemical engineering, you will recognize very quickly that that's not what we're expecting. So this is not useful yet. We have a real big gap between what out-of-the-box language model are able to do and what we actually need in terms of quality to use it in engineering actually at the moment, right? So what you see here is complete bullshit. So this is a bit discouraging. So the question is, what does it take to develop GenAI for our domain? And here it's worth to think a bit high level. Well, what does GenAI actually require? If we look at ChatGPT, they use a lot of data. They represent data as text, and they use some kind of transformer architecture, right? We have also GPU computing, which we need, but it's kind of given by now, right? So these are the 3 main ingredients. So for us, the question is, what do we need in process engineering if we want to develop GenAI for us? So do we need big data? How much? Do we need information representation? How do we need the same models or different? And then we also have this additional domain that is the mechanistic knowledge, the physics, the chemistry, our knowledge and experience. And the question is, how can we get that in? Because that's currently not in models like ChatGPT. But you know, we have it available that's specific to our domain. And the question is, how can we integrate it, make it accessible for the machines as well? So what I would like to do is I would like to walk you a bit through a few of these steps. I don't manage to do all, to give you an idea of what we need to do in order to get it actually, and to have useful GenAI for our domain. So let's start with the big data. And here the question is our domain, chemical engineering, chemical process engineering, actually big data domain? And if you read the articles, the literature, if you talk to people, most people will tell you no. Most people tell you it's not a true big data domain because we have just limited data. We are not like text. You can't mine the whole internet for P&IDs. Or you can do it, you just don't find that many. So this is a point where many people actually stop. And we say, hey, great idea, GenAI in our domain. However, we don't have the data, we can't do it. We need to build specific hybrid models for our applications in order to be reliable and be able to do anything meaningful. And I believe that there's some truth to it in terms that we need to build hybrid models and we should integrate our knowledge. However, what we're missing, I think, is that we actually have quite a bit of data. So if you look around, if you're a chemical engineer, chemical process engineer working on anything in the company, you generate data every day. We're talking about emails, lab books, property data, molecular simulations, flowsheet simulations, flowsheets in general, publications, patents, CFD simulations. You know, there's so much we do every day. And we generate throughout the life cycle of a plant. So why do people say we don't have big data? Why do people say we don't have data at all? I think the point is that we have a lot of data. It's just, it's heterogeneous. It's not findable. It's not easy to use machine learning on. So most people in machine learning community, what they want is, I want my data in a CSV file. I want a list of molecular structures and properties, and then I can run my machine learning model on that. Or nowadays, I want, just give me your text, I will process it. I can use a large language model on that. However, that's not how our domain works. We have our data in random, weird, strange formats distributed everywhere. And we're missing the people in between making the effort to get the data ready for machine learning. And then also develop specialized models that account for our data formats. So that's my personal opinion. And specifically, if I talk about flowsheets, P&IDs, they're mostly hidden in companies like Aramco, for example. You have a lot of P&IDs probably. In the public domain, there's less available. What we do in the research, we mine a lot of data from the internet publications. We download everything that has ever been published in chemical engineering or patented. We automatically find all the images, we automatically extract them. We automatically classify them to have a database of everything that has ever been published, every chemical process essentially. But we also work with companies together and get their P&IDs and PFDs. Now you could say, well, then you have a data set of PFDs, P&IDs, so process flow diagrams. However, there's an issue with this. And the issue is these process flow diagrams, they are not designed for machine learning or even for computer readability or processability, right? They're designed for communication between humans or engineers. So these diagrams are currently mostly PDF documents or even scans. And you can just like give it to machine learning algorithm, expect it to learn. So what we need to do is we need to digitize the information. We need to make it in the machine-readable format. And this is where we are developing a software, actually, digitization companion, where you can read in your P&IDs. And then what we do in the background is we have developed a number of computer vision algorithms that are able to detect all the unit operations, that are able to detect all the lines and their connectivities, all the text, all the tables, and then basically digitize a P&ID automatically so you can extract the actual information content of the P&ID in a smart format. And that can be DXP format with a data standard for P&IDs, or can be CSV depending on what, or JSON, whatever you need, right? And this is really crucial because if you don't have your data in a machine readable format, if it's just a scan or PDF, I don't believe you can do much with it. And we developed this app, and we also have a API. So we plan to integrate that also with existing software. So you can actually digitize your P&IDs automatically. If you're interested in this, it's something that we do in our research at the moment, and we develop. And it's at a stage where we are planning to do a minimal viable product in Q2 next year. So if you're interested, visit our homepage and sign up, then we come back to you and you can try it out as well. Yeah, so we actually have a front end and the model's already ready. It's still quite a bit of software engineering we need to do, and we do here. So once you have your flow sheet in a digital format, the question is, how should you represent it to your machine learning algorithms? So this is about information representation. I believe there's two key formats here we should talk about. There's a graph format, which comes naturally, kind of. So nodes are the equipment, edges are the connections. If you go into more details, you recognize, hey, it's going to get more complex. You're talking about hyper or knowledge graphs with quite complex data models. But there is a smart way to represent this information as graphs. And you can also traverse this graph and save it as a string. If you're a chemist, you probably know Smile strings. So this same idea, but for molecular graphs. And why would we do this? The idea is many of the large language models, the standard transformer, they work on sequential data. So if you want to just use whatever comes from Facebook out of the box, fine-tune it on your data, you have a good chance if you just use a text format as well, right? So I think this text format is a shortcut to get a quick success. The graph format I believe in the long term. In order to make this graph actually happen, what we did is we implemented a graph data model in Python. This has around 500, 600 classes. So it's quite a complex data model. You need that in order to capture complexity of these diagrams. I think that's another reason why there has been less innovations on GenAI, or less quick innovations on GenAI, because the data is just such a pain, right? So you need a lot of domain knowledge to understand what's going on. So what you can do now is we can take this P&ID information and we can build this graph. We can also save this graph in graph databases. So this is an illustration from Neo4j, for example. And of course, you can generate multiple abstractions of these graphs. So you can generate graphs on a higher level. So it's a bit easier to understand for humans and also for machines, actually. And you can arrange all the nodes according to layout of the P&ID, so it's easier to interact with this. So this is an illustration of a high-level graph that we put on top of a P&ID. So it's relatively easy for engineer to understand, hey, what's going on? Is this actually what I want? Where's my information? And so far, we have used standard machine learning to extract the information, but we haven't done any fancy Gen AI yet, right? What you can do is if you have your data machine readable, you can actually connect that automatically or relatively easily to large language models already and interact with a database, right? And this is what we show here in the video. So here we have this P&ID. We translate that to a graph data model, and you can actually navigate in this graph. You can go through the nodes, you can look at the details, look at the specifications. And we connected this graph with a large language model. So you can also interact with the graph in natural language, or with a P&ID actually. And we call that chat P&ID. So what we do here is you can ask questions like, describe the process in P&ID form from inlet to outlet. And you see the large language model is just generating the text relatively quickly. If you go through the details, it's actually referring to the nodes because it has access to the graph. And you can, write text. You can adapt the graph. You can use this interaction. I think we have one other demonstration here, which is just like list all valves. Let me see what's happening. List all valves and their specifications. And now you get a list of all the valves with their specifications. So this is already an advantage and relatively easy once you have your data ready in the right format. However, in the long term, what we want to do is we want to train our own models, right? So we want to train models to help us doing the engineering work. And here the question is, how should our models look like? We have two kind of architectures here that I want to highlight. It's the transformer architecture and the graph neural networks. There's many more, of course, but the main idea is if we have sequential data, like the smiles, like the strings, S-files, string representation of the flow sheets, probably wise to go with the standard transformer architectures. If we encode our information as graphs, would be clever to have a machine learning model that can process graph-like information. And these are usually graph neural network. And then, of course, you can mix and match and recombine. You can have graph neural networks with attention layers, graph transformers. You can start to put in a graph and generate a string. You can have multimodal formulations and so on. So it's a lot of interesting and fun stuff to do here with the models as well. So let's go to one case study at least to show you a bit what you can do already if you put this together, like get the data, digitize it, and train your own model. And I wanted to go on and focus a bit on autocorrection. And here we have twofold approach where we work with rule-based and AI-based methods essentially. The reason is if we look at what's happening in text, that's the same. Like people combine rules and AI-based approaches, and I think there's good reasons for doing that. If we look at the rules first, basically what's happening here is we can formulate rules as graphs as well as rule graphs, and we can run rule inference algorithms on our graphs. So it's easier to understand if you look at an example. So here we have a P&ID as a graph. And if we look at one of the vessels here, for example, what you see is basically just a P&ID representation of a vessel with all the instrumentation, the pipelines, the valves, and so on. And we can encode that as a graph as well. And we have a rule that basically says like, hey, if you have a vessel with a high pressure, you better install a pressure relief valve. And that's a sensible rule. This pressure vessel doesn't have it yet. So what we can do is we can automatically identify that and we can automatically add that and also communicate that to the user, right? We can say, hey, in this vessel, there was no pressure relief valve and that's why I added it here. Or I would suggest to add it here, can you confirm this? And if you do that, this is actually super quick. You can run rules on complex graphs in hundreds of a second. And it's very reliable. If you include a rule here, it will be found 100%, right? So these algorithms are reliable. And we did that on large P&IDs already. However, there's also restrictions to this. And in particular, you need to set up the rules. And they have very narrow scope because the data models are extremely precise. And you need to know the data models extremely precise to set up the rules properly. So this is a bit of a pain point. You actually need clever people that understand both worlds a bit, like the chemical engineering, but also the software part, to be able to implement those rules. And yeah, it's just a pain to do it manually for a large number of rules. But still worth it if you have safety relevant rules that you really need to enforce. And of course, quicker than checking, 2000 P&ID pages or across multiple projects, of course, right? But the big question is, hey, can we automatically find rules without implementing or errors without implementing all these rules manually? And here the hope is really that if we give our machine learning algorithms 1 million P&IDs or 100,000 or 10,000, can we automatically find these outliers? And we did a first approach here as well. So what we did here is we generated actually examples of P&IDs, or I think it's PFDs here, with and without errors. And this was based on synthetic data that we generated. And we fed this data to transformer architecture. So this one was actually based on the string representation of the flow sheets. Now we also did it with graph representations. If you look at just the accuracies, we can see that it actually works quite well already. We need to be careful here because it's only synthetic data. There's less complexity than real P&IDs, but it's proof of concept level. And if you put in a PFD like this one here, what the model would tell you is, hey, there's 2 potential errors, and the potential errors are here. So what the model suggests you to do is add the temperature controller, let me find a laser, around here. Why would you do that? Well, I mean, that's a heat exchanger. This is a coolant probably, or steam to preheat. And then usually you want to control the temperature here, and you can use this flow rate here to do that. And also you can use a pressure controller and this valve here together. Are these actually sensible and good suggestions? We can argue about it. I don't know. Why do I not know? Because, hey, this is not a real P&ID, this is not a real PFD, this is synthetically generated data. And if you really want to make a good decision, you would need to know more about the process. What's going on? What's my goal? What are we producing? What are the pressures actually? And so on. And at the moment, the point is that this model doesn't know it because this model is limited to the topology information. So it's really early stage proof of concept that's not usable in industry yet. We need to get better at representing our data. We need to, develop new model architectures. But I think there's a good chance that we will be able to include this additional information and get the necessary data to get actually useful models in the near future. Okay, so what I showed you are a few applications, right? But what I don't want you to think of is separate applications. Because even though we have separately trained models at the moment, the real magic happens if we start to combine stuff, right? And that's what you see in ChatGPT, for example. ChatGPT learns about, I don't know, English grammar by seeing Chinese documents maybe. And we can do that here as well. We have a lot of synergies. Like if you as a process engineer work on HAZOPs and you find the common error that you should fix, you will consider that in your future development of PFDs or P&IDs. So there are a lot of synergies between these tasks. And of course, there's many more tasks that we need to consider, and there's many more synergies. So the goal is to have actually bigger models that can do multiple of these tasks together, and we leverage all the synergies. And actually what we developed is this pilot process intelligence learning optimization toolbox, where it's not only one big model, but we're talking about multi-agent architectures. So we're developing multiple agents for P&IDs, for reactions, distillation, HAZOPs, and so on. And we actually merge all of them together so they can talk to each other. And they're not only trained machine learning models, they're also able to use tools, databases, and data. So we connect them to simulation environments, to property data, databases, to reaction databases. We give them HAZOP data, reports, lab books, and all of that information. And we also have agents that actually work with time series data, with sensor data, combine that with the P&IDs, and so on. So I think there's a lot we can do when we leverage all of this together. So this is a bright future that we have. Before I stop my presentation, I want to emphasize that all of this is only possible because we work a lot with industry together, and I think this correlation is key, because I learn a lot from industry on actual P&ID development, for example, on the HAZOPs, and they learn a lot from us, and I think it's only possible to develop all this stuff if we in a joint effort, essentially. And here I want to emphasize Linde and Siemens, for example, where we try to go from PFDs to P&IDs. Fluor, where we work on autocorrection of P&IDs. With Shell, we work a lot on hybrid models, and with Danone more on the time series soft sensor data. But all of these are actually in the same direction on this shared vision. So let me conclude a bit. So what I showed you is that digital engineering data is key. So that's my opinion. If you want to do anything new, interesting, amazing in our domain, you need to think about not only text, but beyond that, and we need the engineering data for that. The good news is GenAI can learn from and generate flow sheets. And these flow sheets, P&IDs, PFDs are one of the key documents that we have in our domain. So that's amazing. The collaboration between industry and academia is key to get the success. And I believe this GenAI has really potential to transform the way we do process engineering. So if we look 5 years in the future, I think we will do engineering very differently than from today. Before I stop, I'd like to thank a lot my team for all their hard work, because of course there's a strong team behind this. I'd like to thank you very much for your attention. I'm happy to discuss this talk and answer your questions.